this advanced conduction series. So let us briefly just recall that what we did in the last lecture. So in the last lecture we just completed the basics of the conduction that is required to proceed further into the real life problems. Now we told that why for only an isotropic material the thermal conductivity tensor boils down to some constant into an identity tensor, right? And before that I derived the thermal conduction equation or the heat equation, okay, heat equation for conduction. So from this lecture, it is lecture 7, okay, so this is lecture 7. From this lecture onwards we will explore the various problems of conduction, okay. So let us start with the most basic thing, that is the one dimensional steady state heat transfer, right? So first we will start with number 1, that is one dimensional steady state heat transfer, steady state conduction to be more precise, right? Now I assume that if you have already done your fluid mechanics course, or even if you have done your on I mean just mechanics, that is solid mechanics course, still you should have some concept about these two words, that is one dimensional and steady state. But in the case that you don't know these two words, then I will just uh, briefly describe these two words, okay. So firstly, one dimensional. So as the name suggests, one dimensional means that is we are only concerned about only one direction. So in case of heat transfer, this is nothing but uh, I mean saying that is the so to explain this, let me draw a coordinate axis, okay. So is my coordinate axis, x, and that is y, and that is z, and this is origin, okay. So if I say that my component of the gradient of temperature, this is a vector, so my gradient of temperature is having three components, right? This into ex cap plus this into ey cap, that is the y component, plus the z component, right? Now I am saying that if I am having a particular problem, okay, where I can neglect this term and maybe this term. So then in the yz plane, mark my words carefully, in the yz plane at any point the temperature is not changing. I am repeating, just mark my words, in the yz plane, throughout the yz plane the temperature is constant. So we are only concerned about the uh, variation of temperature in the x direction, right? So then we are only concerned about the variation of the temperature in x direction, and that is nothing but the consideration of one dimensional. Similarly, if only one component of the temperature gradient vector is 0, then we are omitting only one direction. But now in any particular plane, let us say for the time being that our delta t or nabla t z, that is 0, that is the component of the temperature gradient in the z direction is 0. That means we have to be concerned about the variation of temperature in the xy plane. So that is the two-dimensional consideration, right? So I think that is clear. So now let us talk about the steady state thing, right? So what do we mean by steady state? Now, if you just look back to the conduction equation that already we have derived, okay, so the most general form of the conduction equation, just let me copy that. Where was the equation? The most general form of the conduction equation, it is this one. So let me copy this thing. Okay, okay, so here I will, okay, so let me remove this extra marks. Okay, now you see that here, if we write the Fourier's law of heat conduction, if we substitute the heat flux vector with that, then this will be also a function of temperature. But here what we will have is, we will have something like this, that is uh, del qi, okay, del xj, okay, we will have something like this. Or in the most general case, I will show you that how can we have that, del xj, and this k into, or minus k into del t del xj, okay. So we will have this one. Now you see that here it is the gradient with respect to the space. This one is gradient with respect to the space, that is the variation of temperature with respect to the space. And this one is variation of temperature with respect to time, right? For the time being, just don't think about that how I can write this thing. Already I have explained you the basics of the tensor notation, so from that also we can explain it, but I will explain you that how we can write this divergence of heat flux vector in this initial notation, okay. So this is dt. Now just focus on this term, that is the variation of temperature with respect to time. So steady state means at any given position, again mark my words, at any given position the variation with respect to time is not there, then it is called a steady state. Now, it can be the case that at any given position the temperature is not varying, but the other properties or other parameters are varying. So then we can say that the temperature has reached the steady state. But in general, most of the properties simultaneously attain the steady state. So we use the steady state, I mean, with the concept of the system. Okay, we say that the system has reached its steady state. Okay, so steady state means we will not have this term, that is the variation with respect to time. Okay, so firstly the problem will be of a heat conduction in a block. Okay, so this will be a block. So let me write, this is question 1. Okay, so the question 1 is saying that we are having a block. Okay, and in this block we already have uh, said that this is our coordinate axis, x, y, and this is z, and this is our origin. And the block, the the block is of the length L or 2L, where this is the midpoint. So this is L, clear? And this height is H, and in this direction also we are having this one. This block is a 3D block, obviously. Okay, so now this width is W. This width is W. Okay, so this is a 3D block, and the coordinate axis, even though it is not seeming like that, but the coordinate axis is at the geometrical center of the block. Okay, now the problem is that we have to find the temperature distribution in the block, but the assumptions are, I mean, not assumptions, it is given in the problem statement, that is, consider only x direction for heat transfer, heat conduction. Okay, then also it is steady state, the block has reached steady state, then no heat generation. Okay, now if you are a B.Tech student who have already done the heat transfer course, then you already are familiar uh, with this type of very simple problems. But this course is is dedicated not only for a student who is doing the advanced level heat transfer course, but also to the student who is just starting the heat transfer. Okay, so that is why I will explain this kind of simple, I mean very simple uh, problems also with a with an elaborate fashion. Okay, so okay, so in any problem, be it a very simple problem or be it a very hard problem, your first step will be to write the most general form of the conduction equation. Yes, if you are expert in that, then you can skip that thing, but if you are writing an official examination, then you should start with that way. Okay, so what is the most general form of the conduction equation? That is our rho Cv del T del T plus this one minus Q triple prime is equal to 0, right? Okay, now according to the uh, given problem, this is equal to 0 because steady state, right? Because steady state, and this is equal to 0 because it no heat generation. Okay, so that means our equation boils down to this one. Okay, now how can I write this thing? So in a Cartesian coordinate, I can write del qx del x plus del qy del y plus del qz del z. Okay, so just for the confirmation, I hope that you are doing the homeworks and the tasks that I generally give in my lectures, because I will not going to check. I mean, how can I check, obviously? But if you don't do those kind of exercises, then you can have some difficulties in the futures lecture. I mean, yes, I will obviously try to solve every problem from a very basic step, but in some kind of problem, that approach does not make any sense. Okay, so in some kind of problems, I have to skip some very basic steps, otherwise that will take some extra unnecessary time. So those students who are doing those homeworks, they will feel irritation. So and I don't want that. So and I hope that you will be doing that. Now don't think like that, that I am just giving you the homework. Each and every question that I give you, okay, that has a particular intention behind it, that you will develop a particular thinking skill that is required to solve the advanced level problems, not only in conduction but in any problem in thermal and fluids engineering. Okay, so please solve that. Those those few hours will not go in vain, I promise you. Okay, now, okay, now if I say, now by the time being already you are familiar with this notation, right? Already you are familiar with this notation. And if you have already seen the previous lecture, previous two lectures, then you know that I can write this as del qi del xi, right? Or I could have written any other alphabet instead of I, right? Okay. Now, from the Fourier's law of heat conduction, we know that what? Q is equal to, okay, Qi is equal to minus K del T del xi. Okay, that is a is equal to minus K grad T, and this is true only for an isotropic material. So obviously in this problem, so let me just write it, that is isotropic homogeneous material with constant properties. That is, generally the thermal conductivity will change with time, I mean will change with temperature, but here it will not be a function of temperature. Okay, now if I put this thing into this equation, then I will get del del I of minus k del t del xi is equal to 0. And as k is a constant, then I can take out this and I can write this one. Okay, so I can cancel out k, and my final governing equation is del del x I del t del xi is equal to 0. Okay, this is my final governing equation, correct? So in your undergraduate studies, you actually do that control volume approach, and you finally uh, actually arrived in this equation only, right? Okay, so I just proved the initial notation that I wrote before, right? So okay, so now let me again expand this, x square plus okay. So this is the Poisson equation, right? That is the, in the short form I can write this one. Sorry, this is the Laplace equation. So what is Poisson equation? Poisson equation is, this is equal to some constant, and what is Laplace equation? Laplace equation is equal to 0. Okay. So if this is our governing equation, now you see that in the problem it is given that only x direction we have to consider. That means our del t del x is equal to not 0, but our del t del y is equal to del t del z, and that is equal to 0, correct? And applying this into this governing equation, that is this equation, we get this one. And here from this we can directly say that t is only a function of x, because we also know that del t is equal to 0. So t is only a function of x, so that means we can write del t del x is equal to dt dx, right? So the governing equation becomes d2t dx2 is equal to 0. Okay, so this is the governing equation. Okay, now one thing is missing in the problem, that is the boundary conditions, right? So here it is a second order differential equation. Okay, that means I need how many boundary conditions? 2 for space. Okay, so let us see that how many boundary conditions are possibles. Okay, how many boundary condition can be there in the question. Okay, so possible boundary condition. Okay, boundary conditions. The first one is called as the Dirichlet boundary condition. Okay, and it says that the value of the dependent variable is given. Okay, value of the dependent variable is given, that is the Dirichlet boundary condition. Okay, so if we go back to that problem, so let me just copy this diagram, I will explain it again. Let me paste here. Okay, fine. So I can say that at x equal to L, okay, that is this phase, that is this phase, and what is my dependent variable? That is the temperature. So at x equal to L, my T at x equal to L is maybe some T2. Okay, and at this phase, that is at x equal to minus L. Okay, so just let me draw other edges. Okay, Okay, so at x equal to minus L, that is this edge, I am having T at x equal to minus L is equal to maybe T1. Okay, you see that at two x phases I am having the temperature prescribed earlier. Okay, so that is the Dirichlet boundary condition, that is the value of the dependent variable is given, right? Okay, so now the next boundary condition is Neumann. Just check the spelling of Neumann. Okay, I hope it is right. So Neumann boundary condition. Okay, and that is the gradient. Okay, of array. Okay, that is the gradient of the dependent variable is given. Clear? That is the Neumann boundary condition. So if I again take the same diagram here, I think it will be automatically copied. Yes. So then again in this phase, so let me just draw the edges again. Okay, so guys, just wait, my laptop is low on battery. Just let me plug the charger. Okay. I'm sorry for the interruption. Okay. So again at this phase, I will have my del t del x at x equal to L is equal to maybe some constant. Okay, so let me term that as some constant C2, and at this phase, okay, del t del x at x equal to minus L is some constant C1, correct? Now don't foster this misconception that I can have only one boundary condition, only one type of boundary condition in both of the phases. I can have one situation where my t at x equal to L is given as T2, and my del t del x at x equals to minus L is given as some C1 constant. So I can have two types of boundary conditions on two phases, or the more general statement will be any boundary can have any type of boundary conditions. There is no restriction on that. But on a single boundary, you cannot have more than one type of boundary condition. That is, you cannot prescribe heat flux and the temperature at the same phase. If you are prescribing the temperature, then heat flux will be automatically fixed by the arithmetical governing equation. Similarly, if you are fixing the heat flux, then you cannot prescribe any arbitrary temperature on that phase. It will be automatically come out from the governing equation, right? Now, can you see the physical meaning of the Neumann boundary condition for the heat conduction case. That is, you are prescribing the gradient, and the gradient is nothing but the quantity which is directly proportional to the heat flux. So if in any problem the heat flux is given, then if in any problem the heat flux is given, that is as good as giving the Neumann boundary condition. Okay. Now the third one, that is the Robin's boundary condition. Okay, it is also called the mixed, okay, mixed boundary condition. Okay, this says that gradient will be related with the dependent variable. Okay, clear? I think it is not clear. So let me explain this. Let me again just copy the diagram here. Okay, and again let me draw the missing edges. So okay, now let us say that here surrounding the block there is some air. Okay, so there is air surrounding the block. Clear? So these the white marks are denoting air. Clear? So this is air. Everywhere it is air, and this air is having a particular temperature, and I denote this temperature as T ambient. Okay, and it is given that that is the heat transfer coefficient H for the air and the block combination is H. Okay, so if you don't know that what is heat transfer coefficient, so then just for the time being know the equation, that is heat flux is equal to heat transfer coefficient into the temperature difference, heat flux at any wall. Okay, so that will be T wall, and this H is the heat transfer coefficient for the wall air combination, wall air combo. Okay, okay, so in this case you will be given these two things. Okay, you will be given these two things, that is this Ta and H. Okay, so maybe at x equal to L you are given that T is equal to TL or T2, and at x equal to minus L you are given this T ambient and H. So then the heat that is crossing the boundary from the solid, the same heat should be going into the surroundings. Okay, that is there should be continuity of the heat flux, because interface cannot store any heat. Okay, so therefore minus k del T del x at x equal to minus L, this is what the heat flux at x equal to minus L, that is equal to H into T at x equal to minus L minus T ambient. You see that here in this boundary condition, this equation is having both the gradient of the temperature at x equal to minus L and the temperature itself at x equal to minus L. So that is what this statement was telling, that is the gradient. Arey yaar, that is the gradient will be related with the dependent variable. Okay, this is the gradient will be related with the dependent variable. Okay, so these are the boundary conditions. Okay, so your homework will be uh, okay, I will solve the uh, some complicated cases, that is the at one phase. So case 1, okay, case 1. So now we already have the governing equation as our del 2t del x2 is equal to 0. Okay, so case 1 is that t, sorry, t at x equal to minus L is given as t1, and your at x equal to L the wall is subjected to ambient air at temperature T ambient and heat transfer coefficient is equal to H. Okay, this is the case 1, the two boundary condition. One is Dirichlet, another is Robin. Okay, so let us solve that. Okay, so now because our problem is already one dimensional, I am only drawing this one dimension. Okay, that is this one. So here our coordinate axis, that is only x, we don't bother about y, right? So this is x here, and actually we can, this whole line, just let me draw it straight. I think it is straight, but still it is not. Okay, sorry. Okay, doesn't matter. So let me draw the center line here. So this is our origin. This is the origin, and this is the positive x, and this is the negative x. Okay, so here is the L, and this is also L, and at this phase I am having T ambient comma H, that is ambient air, and this phase I am having T is equal to T2. Okay, this is the problem statement. Now how can you write the heat flux, okay, in this phase, in this phase. Okay, for this we will consider a convention. What convention? That is heat. Okay, heat entering into the block or into the system, rather into the system, is positive. Okay, that is, if any heat is entering, then it is positive. Okay, then it is positive, otherwise that is negative. Okay, and we already have another convention, that is positive heat flux, positive heat flux in direction x1 is given as what? Minus k del t del x1. You mark these two statements very carefully. Okay, that is positive heat flux in direction x1 is minus k delta t del x1. That is positive heat flux maybe in direction z is minus k del t del z. Okay, so you see that for this one, how can I write the heat flux now? Okay, now if you assume that the heat flux is going outside the block, heat flux is going outside the block, then you have to write it is negative minus q at x equal to minus L is equal to your H into T wall minus T ambient. Okay, why T wall minus T ambient? Because I am expecting, that is, heat is going from wall to the atmosphere, that is the block to the atmosphere. That means the wall temperature, that is this temperature, sorry, that is this temperature here, that is T at x equal to minus L, this should be greater than T ambient. That means it should be H into T at x equal to minus L minus T ambient. Okay, so this is nothing but T at x equal to L, x equal to minus L, sorry. Now if you follow the second convention here, you have to follow only one, not the both. You can use the second one to check. Okay, so if you follow this convention, then you see that if you write minus k del t del x1, then it is positive heat flux towards the positive x direction. Okay, now I am concerning about heat flux towards negative x direction, that is heat flux towards this direction. That means here will be an extra minus. So if I was telling that I am assuming that the heat is going from atmosphere to the block, that means you see the heat flux direction is towards positive x. So there I should have written minus k del t del x. But because it is towards this direction, I am writing del t del x, that is minus k del t del x into 1 minus, because if you write minus k del t del x, that is heat flux towards positive x. So to denote heat flux towards negative x, you have to write minus of minus k del t del x, that is positive. Okay, so that is equal to your H into, again by the same logic, that is, if heat has to flow from the block to the atmosphere, that means wall temperature must be greater than the ambient temperature. And okay, so this is del T del x1, that is x1 is x only. Okay, and this is at x equal to minus L, and this is also at minus L. Okay, now you see, the moment you write here minus q, okay, the moment you write here minus q, now this q has only definition minus k del T del x. So again this equation also boils down to this. I am explaining again both the approaches because this is very important. In future you will be studying advanced convection heat transfer. So there also this confusion regarding the direction of heat flux is very prevailing. So to avoid that or to master that situation, you have to learn this. Okay, so you could have taken your own convention, that is, my heat entering into the atmosphere is positive. Okay, then also you will get the same thing. Okay, I mean, according to your convention you have to change your sign of heat flux. Okay, so here you have to consider either of these two conventions. So let me explain again these two. Okay, see very carefully. For this, that is, heat is entering into the system is positive. So I am considering for this problem, that is, heat is going to the atmosphere, that is, heat is leaving the system. So these equations, so let me write this. So we consider here we consider here in this problem, okay, in this problem heat is going out from the system to the atmosphere. Okay, and because of that only, if heat has to go from the block to the atmosphere, we know that this T wall must be greater than T ambient. That means heat must be written as H into T wall minus T ambient. Okay, and heat is going outside to the system. That means with respect to the system, I have to write minus q at x equal to minus L, that is minus q at x equal to minus L. Why? Because of this convention and because of this assumption in the problem, we are getting this equation. In the second approach, the positive heat flux in the x1 is given as minus k delta T delta x1. In this problem, we are considering that the heat is going into the negative x direction. So if the positive x direction, in the positive x direction, the heat flux is given as this one minus k delta T del x, then heat flux towards negative x direction will be 1 extra minus multiplied into that. And again by the same logic, that because the heat is flowing from the block to the atmosphere, we are having T at x equal to minus L, that is the T wall is greater than the T ambient. So that is equal to T at x equal to minus L minus Ti into H is equal to minus k delta T delta x at x equal to minus L. Okay, now your homework is here to consider the opposite convention, to consider the opposite assumption, that is, the heat is going into the block, and see, heat is going into the block, and see that if you are getting the same expression, same mathematical expression or not. Okay, you must get the same mathematical expression with the opposite convention also. This is your homework. Okay, if you are not getting that, please comment that in the comment box. I will be clearing that out. Okay, don't worry. Actually, in that case I will make a separate video considering all the homeworks, if not one video then more than one video, to discuss the answers of the problems which you guys are not getting. Okay. Okay, so one boundary condition is this. So let me write it in a concise manner, that is k del t del x at x equal to minus L is equal to h into t at x equal to minus L minus t ambient. This is one, and another boundary condition is t at x equal to L is equal to t2. It is given, and the governing equation is del 2t del x2 equal to 0. Okay, so now just let us solve it. So this will be a constant and this will be c1x plus c2. Now using this governing equation, so using the second governing equation, okay, that is from this 2 we will get t2 is equal to c1l plus c2. Okay, and from these two equations, okay, from these two equations, this and this, we will get k into, okay, so dt dx at x equal to minus L is equal to h into t at x equal to minus L, okay, minus t ambient. Okay, so this is a constant. So here we have the value of dt dx as c1, so let us put that here. So this is c1. Okay, so k into c1 is equal to h into t at x equal to minus L minus ta. So we know that at t at x equal to minus L is nothing but, from this equation, t at x equal to minus L equals to c1 into minus L plus c2. So this will be minus c1L plus c2 minus ta. Okay, so you have two equations. So this will be, okay, c1 into k by h plus c1L, okay, minus c2 plus ta is equal to 0. So c2 minus c1 to k by h plus L is equal to ta. Another equation is c2 plus c1L is equal to t2. Okay, so from these two equations I can multiply 1 minus 1 into the second equation, so then these two will be cancelled out. So then c1 into k by h minus 2L, just don't I mean avoid the algebraic calculations, just please go through the algebraic calculations carefully, because I may have done some mistake in the calculations. Okay, because None of this problem I have solved before in a paper and then I am solving it. I have already just taken this problem in this lecture only. I mean, for this time being, I have just taken this problem. Okay, I have not revised this problem for teaching you. So that is why some algebraic mistakes can be there. Be careful. Okay, so that is equal to Ta minus T2. Okay, so then C1 is equal to Ta minus T2 K by H into this one minus 2L. Okay, so if C1 is this, then from this equation, that is T2 equal to C1L plus C2, we can find C2 equals to T2 minus C1L. Okay, so that is equal to T2 minus Ta minus T2 into L by K by H minus 2L, right? So T2 into K by H minus 2 into T2 into L, okay, minus Ta into L minus plus T2 into L by K by H minus 2L. So here T2 into K by H minus Ta into L minus T2 into L. So I can take the L common here, okay, and I can write it as plus into L. Okay, so K by H minus 2L, right? So this is the C2, and by plugging in this C1 and C2 you can get the temperature distribution. Now you can guess your homework, right? That is to solve all other combinations that can be there. I have solved one of the most toughest combination because of the because of the confusion in the direction of heat flux. Now your homework is to solve all other combinations which are possible. Okay, so maybe in the next lecture we will see some other combination, one more combination that is tough. After that we will consider the case with heat generation. Okay, one dimensional steady state and heat generation. Then further we will move to the two dimensional as well as the unsteady state heat conduction. Okay, then we will go to the Lamont parameter analysis, then we will go to the fin analysis. All those things will be there. Okay, now until that, please do your homework. Okay,